So we're still doing trig and substitution. We're going to be thinking about the types of substitutions that we were doing before trig, before reverse substitution, when we were really focusing on just undoing the chain rule. And we said in those cases, we're really thinking about the chain rule in the forms that we know it, and we want to pick our u to be something that has its derivative there so that we can stuff that derivative that we pulled out back inside. So we're letting our u be one of the g's from this thing. Sometimes those g's, like what we saw in the integral of tangent x and the integral of cotangent x, sometimes those g's are trig functions, and it can be useful to let u equal to a trig function. So let's do a few examples of that. So we will have calculate the following integrals. Following integrals. So we'll start with the first one here, a, the integral of sine of, what am I doing here? Not what I wanted to do. The integral of sine squared of 4x cosine of 4x dx. Okay, so I know that sine squared cosine is not a known form. That's not one of the trig integrals that I know. But when I look at this, two things jump out to me. The first is that, oh, hey, look, I have sine and cosine is the derivative of sine. Oh, hey, sine could also be the derivative of cosine, or negative sine. So first, that we kind of have a function whose derivative is there. And the second thing is that that sine is the thing to the power here. So I could actually rewrite this by moving that power of 2 down to the end. Okay, so that gives me a clue then that a good u here, that I'm probably undoing the first chain rule that we have there, that g to the n, and that the thing that's to the power here is sine of 4x. So I'm going to let u equal to sine of 4x. And then I have du is equal to cosine of 4x times 4, because I have a little chain rule there, dx. If you see sine of 4x and you're like, oh, crap, I don't remember how to do a chain rule with trig, remember you can always do multiple substitutions. You could start by letting u equal to 4x, the thing inside of your trig function, and then just do 2 substitutions. And that would be a perfectly reasonable, valid way to approach this problem. That said, I'm doing it here with 1 substitution, which means I need to multiply by 4 and divide by 4 so that I have my 4 cosine of 4x. Then I'll rewrite this thing, 1 over 4, the integral, that's sine of 4x, that's my u, so u squared du. Oh my gosh, that's a super simple known form. So I have 1 over 4, 1 over 3 u cubed plus c, which gives me 1 over 12 sine cubed of 4x plus c. Boom, that's my answer. Perhaps some of you are wondering if it would be okay to put the power of 3 at the end, and the answer is yes, as long as you remember to put your parentheses. In other words, 1 over 12 sine of 4x, all of that cubed plus c. It's totally fine to write your answer that way as well. Let's do a more challenging one. B. Okay. So here I have the integral, I have the integral of cosine x e to the power of the square root of 1 plus sine x over the square root of 1 plus sine x dx. Okay, so this, I have an e to a power. It probably is the second thing here. So we have we know that letting u equal to the exponent of e is an incredibly useful plan. But more than that, we've also seen that it can be useful to let u equal to the thing under the square root or the whole square root. So in this case, I'm going to let u equal to the whole square root. So I have the square root of 1 plus sine x. Now, with this problem, if you just pick u to be 1 plus sine x, again, totally fine, totally valid way to approach the problem. All that's going to happen is that you're going to have to do multiple substitutions. You'll have to do 2. So it actually might take time as soon as I'm done with this one to show you how that would work out. Okay, so I'm going to let u equal to the square root of 1 plus sine x. Now we've said, to make your life easier, hopefully, I'm immediately going to square both sides. When I let u be a square root, squaring both sides is probably the most efficient way to continue the problem. I don't have a chain rule that I have to do anymore. So now I'm going to have a 2u du over on the left side and a cosine x dx over on the right side. So I took my derivative of both sides, and this is my substitution. So that cosine x dx, good news, I have it there. That cosine x dx, it's not replaced with du, it's replaced with 2u du. And then I know that my u is equal to the square root of 1 plus sine x. So when I have a square root of 1 plus sine x, that's what's going to be replaced with u. So I will have e to the u over u, and then that cosine x dx, that's 2u du. Be really careful about that. It's really easy to accidentally just replace it with du. Make sure if there's a 2u or something over on the left side that you use it. Cancel out my u's. And now this has become a simple known form. So it's just 2e to the u plus a constant, which gives me 2e to the square root of 1 plus sine x plus c, final answer. Okay, so it actually wasn't that hard in the end. Hopefully you guys are getting comfortable with this idea of squaring things when you let u be a square root. So we're going to call this option 1. And we're going to do it just so that you guys can see it happening. Or option 2. And option 2 will be with 2 substitutions. And 2 substitutions, like I said, remember, is useful for avoiding chain rules when you're finding du, or sometimes just to kind of break the problem down into simpler parts so that you can kind of more easily see what the problem's trying to be, where it's going. So here I will let my u equal to just 1 plus sine x, and then du is equal to cosine x dx. I'm going to rewrite the problem. Cosine x e to the square root of 1 plus sine x over the square root of 1 plus sine x dx. Now this time that cosine x dx actually is only being replaced with du, because I just got du is equal to cosine x. This time also, it's just 1 plus sine x, that's u. I'm not including that square root. So I end up with e to the square root of u over the square root of u du, and that is not a known form. So this right here is substitution 1, because now I see that I'm going to need a substitution 2. And we have 2 ideas for picking u going for us here. One, that power of e, the exponent of e is the square root of u. But we've also said if a problem contains a square root, you might as well just let u be that square root. So for my second substitution, we're going to use w now and not u. And we're going to let w equal to the square root of u. But guess what? We're still going to do that technique where we square both sides. When we let w be a square root, always just get rid of it first. So w squared equals to u. So 2w dw is equal to du. And now I'm replacing just that du with 2w dw. This is my sub 2. Okay, so then I end up with, every time I have a square root, I'm just replacing it with w. So I have e to the w over w times 2w dw, and the w's cancel out. So we can say goodbye, goodbye, move that 2 to the outside. Oh, hey, look, I end up with the same simple antiderivative to take. So that's 2e to the w plus a constant, 2e to the square root of u plus c, and then u was 2e to the square root of 1 plus sine x plus c. Final answer, same as when I did it with just one substitution. Either of these, totally valid options. Okay, we're just going to do one more of this type of problem. We're going to look at the integral of e to the x cosecant squared of e to the x over cotangent of e to the x dx. Now, I'm actually just going to immediately do this one with two substitutions. We've seen that when e to the x's are involved, especially when you've got a whole bunch of them, sometimes it can be useful to just be like, hey, I'm going to let u equal e to the x. So we're going to let u equal e to the x here, and therefore du is equal to e to the x dx, which I have, yay, good news. That's my du. And then the other e to the x's just get replaced with u. So this is cosecant squared of u over cotangent of u du. Well, as we can see, that's not a known form. This did not get us to a place where we are capable of just writing down the answer. So we're going to do a second substitution. And here, yes, cosecant is the thing to the power, but the fact that I know that the derivative of cotangent is just negative cosecant squared is really useful in helping me see that a good u here is actually cotangent u. So I'm going to let w equal to cotangent u. So then dw is negative cosecant squared u du. I'm going to multiply by a -1 on the inside and the outside so that I have my dw. And then this becomes negative the integral of 1 over w dw. So I'm just replacing that cotangent u with w. Known form, good news, negative natural log of w plus c, negative natural log of cotangent of u plus c, negative natural log of cotangent of e to the x plus c, final answer. And now I ask you, try to answer the question before I write it down. What substitution could I have done in order to do this with just one substitution? So what would have been the good substitution to finish this in one go? What substitution? With just one substitution. Okay, so hopefully you've thought about it and you've come to the answer u is equal to cotangent of e to the x. So if you want to try to do that substitution, you'll see that it gets through it in just one go. But we have a chain rule here. I have negative cosecant squared of e to the x. I have to remember to pull out that e to the x dx. So the two substitution methods, the one substitution method, either is great. So we got one thing left to do here with trig, and that is to do these trig functions with some bounds. So I'll see you in the next video for bounds.